This is our group's member, Aswad, Ali, Haizi and Alia.
Our group will demonstrate the experiment of hydraulic jump. Firstly, the three parameters that has been considered in this experiment are the opening of sluice gate, the height of the water behind the sluice gate, and the flow rate. For the problem statement, we are assigned to identify the differences between the upstream and downstream depths of flow from the experiment. We also have to measure the values of H, H1 and H2. Based on the depths measured, the specific energy located at upstream and downstream and the power loss due to jump can be calculated. In addition, the head loss and power loss that occur due to hydraulic jump are also to be calculated. Then, based on the Froude number obtained, we can classify the types or categories for the particular hydraulic jump. The experiment is to be carried out over a range of discharge, ensuring behavior over a range of Froude number. The objective of this experiment is to investigate the characteristics of a standing wave hydraulic jump produced when water flows beneath an undershot weir and to observe the flow patterns obtained. These objectives can be supported with 4 relevant and validated sources as shown in the slides.
For the basic concept, I will start with the definition. A hydraulic jump is a sudden increase in the depth of water flow. It occurs when fast-moving water encounters a sudden change in the cross-sectional area of the channel it is flowing through. It occurs when the flow of water is supercritical, which means that the water is flowing faster than the speed of wave. The jump will occur when the water encounters a change in the cross-sectional area of the channel, such as a narrowing or decrease in slope. In this experiment, we aim to investigate the characteristics of a standing wave produced when the water flows beneath an undershot weir and to observe the flow patterns obtained. Hydraulic jump is used in many applications. There are 2 examples they can read on the screen.
Learning outcome. First, students are able to identify and compare the flow upstream and downstream depth of the respectively for the hydraulic jump. Second, students are able to compute the energy dissipated in the jump and power loss at the hydraulic jump section based on the specific energy consideration.
The apparatus for this project is rectangular view, sluice gates, tailgates, and point gauge.
Measure the channel width and height using vernier caliper and ruler.
Put upstream sluice gate and downstream sluice gate.
Switch on the switch. Start the pump and regulate the discharge valve in order to reach the required flow rate.
Measure H0 and H using ruler.
Measure the depths upstream and downstream of the jump, H1 and H2 using point gauge.
Determine the discharge in the channel using the flow meter and recorded time.
The data and analysis for this project, we need to take width, height, length, volume, time, H, H1 and H2. From the data taken, we can find V1 and V2, and then we can find Froude number, F1 and F2, and then we can find E1 and E2 by using formula H plus V power of 2 divided by 2G. And then we can find EM by using formula E1 minus E2. Lastly, we can find P by using the formula rho G Q and multiply EM.
This hydraulic jump experiment was conducted in a rectangular flume with a width of 0.08 meters, a height of 0.102 meters, and a length of 0.345 meters. The opening of the sluice gate, height of the water behind the sluice gate, and flow rate were the 3 parameters that were considered in this experiment. The results of the experiment showed that the power loss and energy dissipated in the jump increased as the discharge increased. This is because the hydraulic jump consumes energy, causing the specific energy of the flow to decrease. This specific energy upstream is lower than the specific energy downstream. The experiment also produced a turbulent flow pattern as the hydraulic jump caused the flow to mix. This is because the hydraulic jump creates turbulence, which is a chaotic motion of fluids that can be very efficient at dissipating energy. The implications of the results are that the hydraulic jump is an effective way to dissipate energy and control sediment transport. For example, the hydraulic jump can be used to dissipate the energy of a river before it reaches a sensitive area such as riverbank or wetland. This can help to prevent erosion and damage to the sensitive area. Lastly, the power loss in this experiment also increased when the discharge increased. This is because the more water that flows through the hydraulic jump, the more energy is dissipated as heat.
In conclusion, the experiment highlights the effectiveness of hydraulic jump as a means of energy dissipation and sediment control. By dissipating energy and creating a turbulent flow pattern, hydraulic jumps can reduce the risk of erosion and damage to sensitive areas. Furthermore, the power loss in the hydraulic jump increases with higher discharges, emphasizing the importance of understanding and managing flow rates for efficient energy dissipation. The main aim of this experiment has been achieved, where the analytical method of determining a hydraulic jump has been observed.